Yeah. So I use intracranial recordings in human epilepsy patients to try and isolate language. I mostly focus on like higher order language, so things like grammar and meaning. So I'm not too focused on things like phonology, speech, those sorts of things. I really care about, like when you parse a sentence, you're doing multiple things. You're doing speech processing, you're doing world knowledge, you're doing attention, situation model construction, all those sorts of things. I'm trying to narrow down on the moments of syntactic inference. So, in other words, not when you're doing semantic inference, like when I say hello or goodbye, or I name a movie, you're doing some sort of semantic inference. But when I say things like, I'll just give an example from one of our papers. We've looked at minimal phrases. So things like red boat, or maybe things like he ran, or, she said, that kind of thing. What's cool about those little things is that even though they're not sentences, what's cool about them is that they actually help you mitigate for a lot of the sentence level problems and sentences. Even though I'm a linguist, I really I kind of hate sentences because they're really problematic. They bring with them all sorts of like non-linguistic processes that I want to isolate. So I'm trying to isolate what happens when you make an inference about constituency structure. So as is often said in linguistics, people like Otto Jespersen, a decade ago, and people like Chomsky and other people have emphasized that language is about making constituency structure, so symbolic structure. It's not just like beads on a strings, like a linear sequence. It really is about building tree structures. So they're kind of hierarchically organized, nested constituents, where relations between elements are not just based on linear adjacency. Like, for example, there are no languages where you have I'm going to do some particular morphological inflection or manipulation on the fifth word of the sentence or the sixth word of the sentence, right? It's never based on those sorts of computations.
Hmm.
It's always based on like structural properties. So, for example, but what's cool about language though is that other aspects of cognition, other cognitive properties can do structure building too, but language turns out to be a weird kind of structure. So, for example, in music, we have a paper where we looked at a professional musician, brain tumor patient in the OR who played a piano when he was undergoing surgery, and we
Hmm.
had electrodes on the surface of the auditory cortex, which closely abuts language regions. So we were able to do a task where we got him to do like a musical task, which is comprehend and play music, but also a language task, which is comprehend and say
Wow.
language. So what we found though is that the electrodes that were sensitive to linguistic structure, and when I say structure, I don't mean linguistic atoms. So there's loads of parts of the brain that respond to words. That happens all, it's very common to find widespread activity for lexical access and lexical processing. But when I say structure, I mean what happens when you combine two words as opposed to combining two other things or things that aren't words, like pseudo words or fake words. Or alternatively, what we did is we looked at different types of sentences that had varying grammatical complexity. So, for example, in some of my work with Carl Friston and Emma Holmes, we've figured out that there is a certain way in which you can formalize like grammatical complexity, in a way that is quite sympathetic to things like minimum description length, Lemp-Poziv complexity, Kolmogorov complexity, all these sorts of compressibility metrics where syntactic complexity essentially amounts to a type of compression, which is very vogue these days in terms of the working memory literature and attention. So anyway, long story short, we did a really nice experiment where we were able to isolate neighboring sites in PSTG, the posterior superior temporal gyrus, which is, like I said, involved in speech, but also language and also music. It's one of those regions where it's kind of there's like a mosaic like tessellation where there's functionally overlapping and specialized and non-specialized regions where you'll get some music selectivity, but also speech selectivity, and then also grammatical, turns out, sites that care about grammar too. So what we showed is that there's this important part of the posterior temporal lobe called the superior temporal sulcus, which has this really interesting organization, which I can maybe talk about later, but it has this organization where electrodes that are sensitive to lexicality, which is whether or not a word is a real word or not. So there are electrodes in PSGS that care if I say hello versus if I say halog, like a fake word. So okay, that's lexicality. But then there's a more interesting component, which is if I can actually derive a constituency structure or not. So for example, if I say red boat versus rulg boat, or if I say red bolg, So in those instances, you're still parsing phonological information, except the phonological information is illegal with respect to searching for a lexical item. Right? There's no lexical concept that refers to that bulk refers to. So what we found is that there are electrodes that specifically cared about phrase meaning, but not lexicality. But those were closely abutting the lexical sensitive sites. So it's like there's a subset of electrodes that really care about constituency structure, or at least the types of meanings that you can only derive from multi-item uh, structures. So, there's loads of forms of compositional meanings that you just can't get from single words. Right? Language allows you to make claims and express beliefs and make inferences that you just can't get with single words. But the reason why I laid all that out is because I said at the beginning there's something weird about language. With music, musical structure, melodic complexity tolerates symmetrical structures very readily. Same with mathematics. Symmetry is tolerated. It's fine. Human language hates symmetry. The syntactic computational procedure that Chomsky calls merge, other people call phrase structure building, just this kind of ability to compose together into structured units, which have a particular like a uh, like a Gorn address going through a tree to search for a node and a mother and sister, right? Some kind of structured tree structure. It turns out that that reduces to a type of symmetry breaking. So, for example, whenever you have two words being merged together, one of them wins. If I say red boat, what does that mean? A red boat is a boat that is red, right? The meaning of red boat is not there is a red-like quality and it just happens to exhibit, boat-like properties or whatever. And it's same with things like, John ran. So John ran is a verb phrase, not a noun phrase. So the meaning of John ran is that there was an event of running and John was its participant. It doesn't mean that there's a special kind of John who exhibits running, properties. So in language, whenever you do things, whenever you merge things together, there's always a winning node. There's always an item that projects what's called the head of the phrase. So noun phrase versus verb phrase. And what's cool about that is that even though other cognitive processes, higher order forms of symbolic thought like math and music and morality have, symbolic properties, language seems to be symbolic in a very unique way, in that there's a specific algorithm that, for whatever reason, seems to work across languages, whereby units are assembled into trees which are labeled. And you don't get that with other non-human cognition as well, but also non-linguistic properties. So what I've been trying to do is say, okay, if that's if that's the definition of language that we're taking, which is it is some kind of computational system that has this weird symmetry breaking algorithm, maybe we could use that potentially as an indication of how the brain might solve language. There's no necessary connection. There's no necessary reason, whatsoever why there should be a connection, but I think there probably is. So what I've been trying to do is some of these algebraic properties of syntax that I'm talking about. I mentioned hierarchical organization. Other things are like non-associativity. For example, if I say old men and women, that could mean old men and women, where the women are young, or it could mean old men and women, where old takes scope over men and women, and it modifies the entire noun phrase, the conjunct phrase, men and women. So that's a very obvious example, very simple example, but it's a very mysterious example where you have a linear set of objects, but multiple structurally distinct interpretations. So the brain has to have some kind of, well, the mind at least have to have some kind of algorithm that enforces non-associativity. And then there's another property, commutativity, which is probably more related to the underlying knowledge of language. But I'll just briefly mention this with respect to how it functions in language. So we know that across languages, the way Italian speakers, Spanish speakers, Japanese speakers, and English speakers express the meaning of certain concepts may differ in terms of their morphophonological realization, in terms of the surface form. So, maybe the noun comes at the beginning, maybe the verb comes at the beginning, right? Maybe the object comes at the beginning. But the underlying coordinates in conceptual space, I suppose, are kind of identical across languages, right? The Japanese speakers know what a red boat is. English speakers know what a red boat is, even if they express it in completely different ways. So there's some kind of underlying algorithm that doesn't really care about the order in which words are placed underlyingly, even though you may express it in the surface form in a completely different linear way. So there's a distinction, in other words, between the surface form of language, like the corpus or the behavior, the outward behavior, and the underlying computation. And there's so many examples of that. If I say something like, so I maybe we can talk about large language models too, but in some of my work I've been probing to what extent large language models respect these algebraic properties of language. Maybe they don't respect them. And what I found, what me and Gary Marcus, Evelina Levada, Vittoria Dentella, and a bunch of other people have found is that these large language models don't really respect what I just mentioned, this brain tumor patient respecting in the OR. His brain very much respected that distinction. These large language models don't really respect a distinction between meaning and structure, whereby in language you have structural configurations that often inform the meaning, but we can make a distinction between those two things. Like I said, old men and women. Large language models are not very good at that. They're very good at generating coherent prose, but if you probe them in very delicate ways, they're often unable to really figure out and make a distinction between this is a structural configuration and there's a separate semantic interpretation that is maybe informed by the structure, but it is in principle separate. So large language models don't really show a distinction for that. And they also don't show when you do brain, these alignments between LLM embeddings and neural recordings. What's a bit suspicious in the last few months, only the last few months, there's a lot of work showing that despite the last 3 years, there's a lot of celebration about how large language models, align with brain behavior. More recently, a lot of work has shown, well, two things. I guess maybe just give you two examples. One example is they resolve best and they predict activity best in non-language cortex, which is a bit of a problem. You would expect them, if they were large language models and not large corpus models, which is what they actually are, then you would expect alignment with language cortex. Turns out not to be the case. Also, a lot of the previous work that's shown alignments between the vector math of LLMs and the neural activity profile in fMRI or MEG or intracranial recordings. A lot of it is driven by overlooked confounds. So things like word rate presentation, like ba-dum, 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 like the rhythm at which words are presented turns out to explain a lot of these effects, which is, I think, a big problem. But so just to kind of give you a more general perspective, I'm trying to figure out, okay, if these are the algebraic properties of language, maybe the brain has a potential mechanism or quasi-mechanistic type of causal structure, some kind of process in which the brain can neurally enforce these sorts of properties like non-associativity during parsing, and to ensure that a particular parse is read out correctly, as opposed to just linear chunking. There's lots of proposals in the literature to do with cross-frequency coupling and brain waves and oscillations, whereby people have tried to explain memory and sequence processing in terms of those dynamics, right? Where a low frequency component might be able to coordinate and dictate the firing patterns of like local assemblies. And that can maybe provide some insight into how the brain manages like linear sequences. But then, of course, like I just said, language is forced to be a linear sequence because when I'm speaking to you, I'm not speaking in parallel. I'm speaking in serially. The serial order is reconfigured and parsed by the brain into a structured form. So there's many examples that I can give you just to really emphasize this. I asked ChatGPT a sentence, which was, I gave it the sentence, the mechanic who fixed the car carefully packed his tools. And then I said, what did he do carefully? So the mechanic who fixed the car carefully packed his tools. The word carefully can modify two things. It could mean the mechanic who fixed the car carefully packed his tools, or it can mean the mechanic who fixed the car carefully packed his tools. So we have a carefully packed his tools, or he carefully fixed the car. And the large language models, because they're driven by statistical patterns, they just say, no, you would never say that. Right, it's just not free. It's not. People just don't commonly do that. So therefore, the interpretation has to be that he carefully packed his tools. It cannot mean that he carefully fixed the car, even though structurally, when a human being passes that sentence, yes, of course, it's true that. In fact, when I posted this on Twitter, Gary Kasparov retweeted saying that I was wrong because human beings take into consider context and nuance and all these sorts of things, and that's obviously true in parsing. But when I just give you the sentence, the mechanic who fixed the car carefully packed his tools, with no additional information, you can make the inference that carefully can modify two things. yes, it's true that adding a comma or adding a pause or adding intonation or standing in a auto shop or standing next to a mechanic, these things would allow you to converge on the meaning more efficiently. But at its purest form, the sentence string can be parsed in multiple different ways. So I've tried to think of like, okay, what are the relevant scales of neurobiological organizational complexity that can provide adequate explanatory power for distinct levels of linguistic structure? So I have this, what I call my Rose model, where I try and negotiate these levels of linguistic structure from phonology to meaning to grammar across like single cell level, local field potential level, global inter neuronal synchronization properties of like phase synchronization and traveling waves, these sorts of things. And I've kind of arrived at the conclusion, similar to what people like L. Miller have come to, which is that there really is no syntax cell. Right? So there's a lot of evidence for this. Cells don't really causally anchor a lot of properties of information processing. Like what drives these global, more complex syntactic inferences, which of course, like I said, these inferences are made after you've assembled multiple features from multiple concepts. Like you don't just go straight to syntax. In order to get to syntax, you have to go through phonology and morphology and other properties of words to get to that syntactic grammatical inference. So it turns out that I think the evidence is really pointing towards a system of phase amplitude coupling and cross frequency coupling codes which coordinate and enforce these sorts of algebraic properties like non-associativity. And in my Rose paper, I detail like some ways to derive that. But there's really good evidence. I can just give you one example. There was a paper that came out in December from Stan Haynes' group in France, and they had 21 acute awake neurosurgical patients with single units, right? So these are patients in the OR, awake doing some sort of language tasks just before or after surgery. And the language tasks were like language comprehension, sentence repetition, auditory naming, these sorts of things where you just make people attend to linguistic structure or semantic structure. And they had across these 21 patients, they had 1,000 good units across 21 patients, right? Of 1,000 units, meaning they were detecting activity from 1,000 cells. Of these 1,000 units, there were hundreds that showed sensitivity to phonological structure, so pieces of phonological information and acoustic phonetic information as well. There were hundreds of units that showed sensitivity to semantic features too. But there were 0 units out of the 1,000, literally 0 units that showed any interest in any syntactic information, any structural information. So I think there's a big rush in the field these days to everybody wants access to single units in humans, but I think it's potentially it's an important part of the puzzle. But I think the story of how these complex syntactic inferences are made, I don't think we're going to find a Chomsky neuron, for example. That's what I'm saying essentially. I don't think we're going to find that. So that's kind of the motivation for where I am right now. Like I've done these intracranial recordings, I've published the experimental reports, but now I'm trying to take a step back and think theoretically, how can we organize this research into a way which not only accords with what we know in neighboring literatures, but also in ways that objectively enforce and respect the known algebraic properties of human language. And like I said at the beginning, caveat, if I'm wrong about these algebraic properties of language, then these other theories will also be wrong too. But I think the empirical evidence is really pointing towards where in the neural complexity hierarchy, organizational hierarchy, we're going to find sensitivity to signatures of syntax. And it looks to be not at the single unit level. Yeah.
Super, super interesting. So I have a whole bunch of questions. First of all, when you said you analyzed LLMs, what exactly do you analyze in an LLM? Is it just the text output, or do you put electrodes in it, then look at inner layers, or like how do you actually do it?
Yeah, so many other groups have done the latter to try and causally probe and lesion
Mm.
particular aspects of the models to see when they break down. The work that has done that, the best work that I know of it is at NYU with Tal Linzen. So Tal's shown that these systems have, unlike humans, they have an immediate bias for imposing linear rules. As in, when they try and resolve dependencies between non-local elements in a sentence, so the keys to the cabinet are on the table versus the keys to the cabinet is on the table, there's a violation. it turns out they will always try and enforce a linear rule to figure out that parse. Whereas humans kind of do the opposite. Like since infancy, there's a lot of evidence that almost as soon as possible, potentially even in the womb, infants are trying to make these structural grammatical inferences as opposed to linear inferences. Now, there's a controversial question, which is maybe these large language models do at some point learn something like a rule of grammar. Um, well, if they do it in a very different way that humans do. And humans have the kind of opposite bias, right? We have an immediate bias to impose structure. The large language models really don't. And I'm very doubtful and skeptical that they do learn anything like an actual linguistic rule. Like a lot of the things that look like rules turn out to be things that, like heuristics and what have you, that can also satisfy very different types of structures that a human being would not count as grammatical or legal language, but which an artificial model would be able to learn no problem. So they can learn things that no human being would be able to parse. Yeah,
I see. Yeah. I mean, one reason I ask is that we study diverse intelligence and all kinds of weird substrates, right? So cells and
yeah,
tissues and embryos and things. And so one of the things that I've often said is, okay, many, if not most of the things that people study in cognitive science, we found these in other substrates, but not language, right? I don't have any evidence for anything that's language. But it occurs to me that, I mean, we haven't looked very hard, and I don't really know how to recognize it. And so I'd love to think that through with you a little bit. How would you, what would be a signature if you had a data stream, and this might be, I don't know, calcium signaling from a xenobot, or it might be some kind of a bioelectric signature from a cultured
yeah.
organ, or whatever, right? So you have some sort of data stream. Do you think there are any signatures to look for that would suggest, wait a minute, there's a structured grammar here, as opposed to simpler things that aren't considered, language?
Yeah,
Well,
no, that's an excellent question. In my roast model, I emphasize very much this kind of oscillatory top-down code that involves like coordinating units into structured ensembles. We really don't know enough about how individual representations, like lexical items, are represented. Like I said, I suspect there's some kind of spiking code, right? Some kind of like local code where which individual neurons express certain properties that conspire into a concept. So John is composed of like male, animate, human, etc. All those features are probably stored locally and maintained in cells. And um, well, let me give you one example. How I can kind of equate this maybe. Uh, Matilda Marcoli, who's a mathematician in Caltech, and Robert Berwick, who's a computer science at MIT, they had a paper a couple of months ago where they looked at these necessary features of language, like the non-associativity, the structured expression parsing, the kind of recursive nature of language. And what they did is they said, okay, here's this mathematical. They cashed out in category theory instead of set theory, but they said here's this necessary features of language. The problem with the LLM approach and other approaches like it is that if they do arise at a kind of language-like representation, it's not necessitated. It's kind of by accident. It's it just happens to emerge in that kind of way, and that's not what we want because we know that all inference necessarily emerge at the same type of grammatical inference very early on. But what they showed though is that the mathematics of formalizing syntactic structure is you can draw a direct line of communication between the way they formalized syntactic inferences and things like phase synchronization. It was much easier to draw a sympathy between those sorts of neural measurements than it was some kind of a lower order spiking syntax. So I think again, which is an indirect way of answering your question, maybe, but I think that's the kind of perspective that I take. I think I'm not a fan of this kind of data-driven, so-called theory-neutral neuroscience, where we'll just kind of look at the brain and somehow language will just emerge if we understand lower level properties well enough. I think the evidence for downwards causation here, the evidence for other sorts of causal structures, relevant causal structures in the brain. People like Lauren Ross have emphasized, as you know, things like cascades, pathways, topological structures, causal and non-causal entities that I think can provide better explanatory power potentially for human language than whatever you might consider, what most people would consider a lower order physical neural mechanism. Now, I'm not averse to lower level physical neural mechanism. I think they're great, but what I'm trying to argue with the example I just gave with the category theoretic definition of a phrase structure is that I think it points to the mathematics points towards particular modes of neural organization, and I think that's really exciting and away from others. So, in other words, if that's what you want from a computational theory, right? That's what David Marr tried to achieve. You have the computational, algorithmic, and implementational. If you can successfully formulate the computational level in such a way that it helps you narrow down the searchlight for the implementational level, then that's fantastic. If you're able to do the opposite as well, that's also fantastic. But I don't see any evidence of the opposite direction happening, right? I don't see any evidence of like focusing on a super lower order properties of neural function, and then somehow the example that I gave about red boat, us being able to understand how that works in the brain just emerging. I think we have to start from this higher order algebraic description, and I think mathematical models are the only really way ultimately to capture these things properly, and then use that as a window into how the brain might respect it too. That's an assumption. It follows a long tradition in philosophy of science. It could also be wrong, obviously, naturally. But so I don't, what I'm trying to say is based based on what we know about human language, we can now begin to narrow down on potential neural candidates, which would also potentially, buy you a way into figuring out if non-human animals also express those sorts of properties. But behaviorally, the evidence I think is fairly strong that you're unlikely to find that. So there was a interesting conversation between Richard Dawkins and Steven Pinker maybe about a year ago. And obviously Dawkins is a arch like neo-Darwinian synthesist kind of guy. Pinker is too, I suppose. But Pinker was saying that it's likely that this property that I just mentioned emerged gradually, whereas other people, other linguists in the field have argued that you either have this computation or you don't. So this computation of being able to form an unbounded array of hierarchically structured expressions, this merge computation in syntax, you either have that or you don't. There's no half merge, right? There's no 75% merge. You either have it or you don't. It's a discrete operation that it requires like some kind of drastic, I'm not sure how you'd express it, some kind of phase transition or something in the way that the brain does computation, which I think explains a lot of the evolutionary evidence, related to the Great Leap Forward and all these sorts of things. Anyway, but so Dawkins surprisingly said, so Pinker was trashing this saltationist type, formalist perspective, and he was saying, no, it has to be gradual. Dawkins said, well, no, it doesn't actually. Like mathematically, there's no real way to show that the way humans make recursive syntactic inferences is a gradual thing. Like, how do you do that? Do you have like a proto version of syntax? And do you start with one word and then two words and three words? Like I said, that's not how it works because syntax it doesn't care about linear stuff. It's a structured hierarchical system. So it's difficult to think how that emerged. And I realize I'm turning the conversation wildly in a different direction, but it's difficult to think how that could have emerged gradually. And the reason why I say that is because I think that the evolutionary texture of that neural code, I think can maybe be relevant to how we do neuroscience here. In other words, which types of ancient or non-ancient or areas of the cortex and so on that we can target based on how the brain is organized. So there's one interesting piece of evidence from the arcuate fasciculus, the white matter tract that connects posterior temporal to inferior frontal. In non-human primates, the arcuate fasciculus is really just like this shape. It just goes from one curve to another. In humans, it's almost like an entire loop, like it's a loop structure where it kind of cycles back in on itself. And some linguists have argued that that physical component, that the nature that the arcuate fasciculus is now organized, could potentially help with this kind of looped recursive operation where you're kind of embedding phrases inside of phrases inside of phrases instead of just doing one particular search. So a lot of non-human primates, in some of my papers previously, a lot of non-human primates can do basic morphology. They can do hock and hock-oo and crack-oo, where you add this oo morpheme as an emphasizer. So that looks a little bit like morphology, like they're kind of adding an element and then adding another small element. But it's not compositional morphosyntax. It is just linear morpho. They are just combining one thing and saying, okay, here's another element. I want to emphasize it. So like there's an eagle, there's a land-based predator, there's an airborne predator. He's either close to me or he's far away, that type of thing. You don't really get anything beyond that. Whereas in humans, you go from that minimal compositional scheme to the full expressive power of David Foster Wallace, James Joyce, Shakespeare. Like there's no middle ground. There's no gradualist perspective here, right?
I mean, so that's very interesting. I was going to add, that was going to be my next question is to what extent can this be derived or even defined in analog computation? So if we had right, and I found one paper. I mean, this stuff is somewhat beyond me, but I did find one
Yep.
paper where somebody was trying to derive this hierarchy from analog, on top of analog computation. And I just, I wonder if it is binary, as you say. So we literally then think as we look at the evolutionary lineage, like there were some parents who couldn't do it, and then they had a kid who could do the whole thing, right?
Yes.
That's the claim.
Yeah. Yeah. There's no other way around that, I think. Um, so in the literature, some people have called that person Prometheus, the first human that had this merge capacity. And what's interesting about it is that so I had a paper in 2019 called No Country for Older One Men, where I chart a lot of the anthropological and paleoanthropological evidence. And what's interesting is you see the emergence of these different higher order symbolic. I mean, you probably know a lot more about this than I do, but from what I read, you see the emergence in the historical record of music, math, art, language, kind of at different punctuated moments. So what probably happened is that you had this human being, and he was able to execute this merge type operation endogenously, right, internally. And it was originally a conceptual. The game was a conceptual game. Later, there must have been a way whereby this computation was hooked up to external systems, so hooked up potentially to sounds or signs. Some people think song came first and sign language, and other people think other things. But maybe mathematics, maybe morality, probably morality, right? Theory of mind, things like that. I know that, he knows that, she knows that, that type of thing. But whatever the case, there was a way in which this what the genuine language, the core language faculty, which is just this ability to create an unbounded array of hierarchical expressions, was interfaced with different extra linguistic components over that 200,000 year period. And now you have modern human beings, whereby we have this symbolic capacity to use language to improve and enhance all sorts of different cognitive aspects. Now, there are some people in literature who disagree with that for the following reasons. They say, look, you have all these stroke patients, and my wife is one of them, by the way. You have all these stroke patients, and they when they lose language, they seem to do just fine with thinking. Thinking meaning all sorts of general cognitive tasks.
Yeah.
That's perfectly true, but nobody would claim that vision is not a sensory system if somebody who's blind but they're still able to taste and hear. Vision is a sensory system, even if it's knocked out, and language is still a thought system, even if when it's knocked out, not all of thought is gone. So there's no reason why knocking out language should knock out all of human cognition. That would be a very poorly designed system. There are certain forms of higher order thought, mainly to do with epistemological inferences like belief and attitude and mood and those sorts of things that you can make with language. And language very much helps with that kind of self-referential, hierarchical, organizational aspect of language. Even if aphasia patients technically pass all of these general cognitive batteries, right, there are still potential deficits there. But so that's kind of the general perspective that I would give. And it also segues into a secondary critique, which is that, okay, if that's how language evolved, and if this is how language is implemented in the brain as well, if that's how language evolved, then communication must be a tertiary component of language, right? Not even secondary, because secondary, it would just be externalization, just expressing language in some way, like putting language out there in the world. But communication is a subset of externalization, right? So most of our use of language, the way we use it every day, this is the point that Chomsky's made very, very well a number of times. When we use language, we often just use it to think to ourselves and meditate and plan and reflect. and brew over thoughts and strategize and things like that. Every now and then we talk to other people, but it's not the overwhelming use of language, right? And even when we talk to other people, it's often just small talk and social grooming and all that sort of stuff. Using language to actually communicate with another human being is maybe not as common as a lot of people intuitively think. And I think the reason why that's important is because I had a paper in 2020 in the journal Glossa where I looked at, okay, what are the predictions of that? Right? Are we doing philosophy or are we doing, science? The predictions are that if you look at the formal structure of language, the way that the syntax and semantics interface, that would suggest that language is maybe optimized for constructing, providing instructions to conceptual systems, and not for expressing unambiguous, transparent, rapid thoughts to other human beings. Turns out that is, I think, other people disagree, but I think you can show that quite nicely with the nature of certain grammatical rules and processes just are terrible for communication. There's all sorts of ambiguity and terrible, awful things. But it's excellent for thinking. It's excellent to organize structured symbolic thought.
Yeah, yeah, interesting. So do you think that okay, what's the current thinking on how much of that structure is learned versus inborn versus
Mm,
determined by facts of mathematics, like the
yeah,
those like where do you think it,
yeah.
it comes from?
Well, exactly what you just lined out is exactly the right way people are thinking about it. When you say determined by mathematics and laws of physics and things like that, that's an excellent question. There's some. This is what my paper with Friston and Holmes was about. There's some indication that whatever the computation is, it seems to be highly efficient. Right? There's an efficiency to the structured formation of thoughts. Okay, I won't go into details. You can okay, but so that takes care of the nature of the computation. What else is innate? Well, so people like Charles Yang at UPenn and other people who study language development and acquisition, there's two camps right now. One camp says that there's basically nothing innate. It's all just domain general learning and a constellation of generic non-linguistic factors that just accidentally converge and across all human infants across all history to the same syntactic inferences. It's definitely possible. The other camp says that there is a unique component to language, and in fact, my Rose paper is meant to be the beginnings. The tentative suggestion is that it forms a universal neural grammar, as in there's a neural code for language that gets you the way to neurally enforce the non-associative and commutative aspects of this structure building computation. But what exactly is innate? So people like Charles Yang think that there is a structure-dependent rule bias, whereby when you parse information that happens to be relevant for language, you realize that the rules are not going to be linear. There's going to be you're going to infer a structure, and then the rules operate on that structure, as opposed to the rules operating on the linear surface elements. So, like I said, the example I gave about the mechanic fixing the car, for example, the way you parse that is through structural information. Or if you say, I watched a movie with Jim Carrey, for example, that could mean you watched The Truman Show, or you sat next to Jim Carrey and you physically watched the movie. Right? The way that you parse these structures is just from very, very, very early age. In fact, there was a paper in PNAS in 2021, I think, which showed that even up to 18-month-old infants show some evidence that they are sensitive to extremely complex syntactic rules, not basic ones like red boat or John ran versus John runs, but like non-local syntactic rules. So it's like, which book did Mary say that John read type of thing, where there's multiple intervening elements and the relations between non-local, distal elements. 18-month-old infants show some sensitivity or some kind of like recognition, if you like, of those structural violations. And that's very wild. It goes back to what Chomsky talked about with the poverty of the stimulus, right? The kids just don't have enough positive evidence to arrive and converge on that route. So anyway, to answer your question, there's some kind of structure dependent rule or bias, right? The machine learning people would call it, some kind of inductive bias or whatever. And then there are also some very specific domain general learning rules. Charles Yang talks about a few the tolerance principle and the subset principle and some other sorts of mathematical learning rules where you kind of efficient domain general learning rules. And even people like Stephen Piantadosi, I think, agree here, where there are some kind of fixed and rigorous domain general learning rules in addition to at least one very minimum language-specific rule, which is structure dependence. And like I said, I just don't know. I don't see the evidence empirically, and I don't see the mathematical way to negotiate these structure-dependent hierarchical recursive rules in a domain general framing of learning. Yeah.
Yeah. I mean, very interesting stuff. I think uh, we're studying the uh, communication both within and between some very unusual and different creatures. So
Mm.
we make some synthetic life forms. We look at cells and tissues and organs and things like that. And some of what we're doing is developing interfaces to communicate with them via language. So
Okay.
using AI to talk to your liver, that kind of stuff.
Okay.
Like,
Yeah.
I mean, well, what does it know about? Well, it knows about all kinds of physiological states and various other problem solving things that it does. And so we can put a language interface on top of that could give great access both to what it knows and then to actually ask it to do things and things like that.
But so you're trying to figure out a way to generate a more structured like grammar, if you like, to communicate with the endogenous organization of these systems, right? Like figure out
Well,
what.
these are two separate things which may or may not go
Mm,
together. I don't know, right?
mm,
So one set of projects is to find out what is the internal what's the structure that the system uses internally to store information and communicate inside of itself between its
okay.
parts, which may or may not have anything to do with the grammar.
Yeah.
The other part is using various AI tools to put something on top of them that may not be endogenous at all, but that would allow humans, whether the liver's owner or a doctor or whoever,
Yeah.
to actually exchange information in a format that we can understand.
Yeah. What I find cool in this connection is like um uh well it may seem intuitive. A lot of these things that seem intuitive. So like I mean all animals communicate, right? Like all organisms have some kind of mode of communication. Um I think the emphasis in the literature, there's been a mistake to emphasize the communicative role of language over its inferential role, as I've said, right? But also, I mean, this applies for everything. Like all of our intuitions about, I mean, this is what Newton proved, right? Our intuitions about, our folk psychology intuitions about mass and motion were, of course, completely wrong. And I think that's also true of language, though, too. Our intuitions about language, a lot of people get into the field of neurobiology of language and have intuitions about what language is and how it should operate. But those intuitions turn out to be true. And that was also the case with like all the three major branches of philosophy, right? Like all our intuitions about epistemology, that no statement can be true or false at the same time. Nope, that turns out to be true. Our intuitions about ethics, that reducing pain and suffering, and increasing happiness is like the primary guiding principle of living a good life. No, I think that's also wrong. That's too simplistic. Our intuitions about metaphysics, that everything must have a sufficient cause or reason, right? Leibniz's principle of sufficient reason. That also turns out to be false, right? As people like uh, uh, John Conway and Simon Koshin might have shown with their free will theorem and things like that. So I think all these big intuitions that we bring to the table, we often convince ourselves that we no longer have them, and that we're doing good science. But I think the proof is in the pudding and the proof is in the mathematics, right? If you can show that all these computations that I've been talking about are not in fact needed to be binary or necessary features of language processing in the brain and acquisition, then fine. Then we can talk more about large language models and how they can help. How they can help me is very different from how they can help you, of course, right?
Yeah.
But like I said, it's a it's a tricky issue. So like what one cool paper that came out recently was that showing that large language models tend, when they do manipulate information creatively, they tend to manipulate noun related information and not verb related information. So, which is not what humans do, right? Because nouns encode some lexicosemantic features, but verbs encode the core properties of grammar, right? With verbs, you get mood, tense, aspect. You can establish predicate arguments and things like that. Like verbs are what do the actual syntactic, grammatical inferences in sentences. Nouns don't really do a lot of that. They contribute to agreement and what have you. But it's a bit suspicious that large language models are syntactically creative with respect to nouns, but not verbs. So I think a lot of these things have to be, whenever we use these artificial large language models, we have to realize that they are, again, large corpus models. They're not, they don't know language. They know how to make what Apple AI called in June sophisticated pattern matching, right? They're very good at sophisticated pattern matching. So it may be good for certain, in fact, one good use that they do have, I think, is in clinical linguistics. Like LLMs seem to turn out to be very good at diagnosing and predicting like language deficits in certain clinical populations. That's a pragmatic use that they have. That's like a pragmatic, practical, clinical engineering type goal, which is of course not the same thing as LLMs. Just don't help narrow down like causal mechanistic neural functions. I don't think. So that would be my kind of skeptical take on how to use these things. Like based on how they actually are designed and what they're good at, you can use them, but not to. I wouldn't for language again. I never would consider replacing my linguistic theory with large language models, which is what many people in the field these days are actively trying to do. They're actively trying to say, get rid of linguistic theory. Large language models do linguistic theory better than linguists. These are literal quotes from the field, and we should just replace our understanding of how the brain and mind execute language with whatever large language models happen to give us. And I think that's a big mistake.
Hmm. Yeah.
Yeah. And then they also fail at compositional things too. Like if you just ask, we have papers showing that if you ask DALL-E to generate images that have compositional meanings, they break down straight away. So draw. The woman did not. One woman had glasses, and the other woman did not have glasses. It'll just show a picture with two women wearing glasses or something. But anyway, so do you have much of a with respect to the neural kind of space, right? So I'm interested in like the power of like electric fields in the brain and how they causally anchor a lot of information processing and a lot of how so-called slow oscillations, low oscillations actually drive a lot of these inferences.
Yeah.
How increasing evidence suggests that, like I said, spikes just don't really causally anchor information processing. Electric fields like travel like at insane speeds, etc., etc. All the evidence that is used for like whenever I talk to oscillation about oscillations to people, a lot of the reaction is like, well, what kind of causal evidence do you have, right? Um, but you could also say the same thing for the spike people. Like, what kind of causal evidence do you have that spikes drive linguistic, semantic, syntactic inferences? Oh, well, we stimulated this electrode in posterior temporal cortex, and the patient was unable to speak, or we stimulated this electrode in frontal cortex, and the monkey moved its eye, or whatever. And it's like, okay, yeah, like you obviously disrupted that aspect of the brain, but you also disrupted local field potentials and oscillations too by doing that. It's very difficult for me to. But do you have intuitions? Are you as sympathetic as I am to the kind of downward causation type of thing? And
Yeah, absolutely. And what we study are the kind of evolutionary precursors to what goes on in the brain. I mean,
mm,
cells have been doing those kinds of things long before there were recognizable neurons or brains, right? This is like super ancient stuff, starting from the time of bacterial biofilms, using bioelectrics as a kind of cognitive glue, basically to bind competent subunits together into a collective that is navigating problem spaces that the individuals couldn't do.
okay.
And so, there are some spiking phenomena, but the vast majority of it is not. These are slow analog changes, and there are spatial patterns that encode basically. We have this tool. I used to have my students do this by hand, but now we made a tool to do it. You can take almost any neuroscience paper and put it into Microsoft Word and just
Mm,
do a find replace. And
mm,
anytime it says cell, anytime it says neuron, you just say cell. And
mm,
anytime it says millisecond, you say hour. And you get yourself a developmental biology paper because basically almost like all the same stuff carries over. It's just a different problem space that
mm,
they're navigating. Instead of
mm,
three-dimensional space, they're navigating anatomical morphous space. And so we find memory and learning, we find mistaken perceptions, we find active inference, we find perceptual bistability, we find rewritable goal set points that are actually counterfactual representations. So we can
yeah.
make a worm that has a representative. We can see it because we can do the imaging now of what what it would do if it got injured in the future, and we can change it.
Mm,
And
mm,
what it would do is not what it's doing now. It's a fictitious, like it's not a it's a it's a two-headed pattern, whereas the worm only has one head. And this is a pattern that it will use in the future if it needs it. But right now, it's like a latent, it's like a latent memory
Interesting.
that doesn't match. It's sort of, I see it as a very primitive beginning of this kind of mental time travel idea that you can represent states that are not happening right now. Like this is
Yep.
it already kind of does that. And
Yep.
so a lot of this is, yeah, these spatial, I mean, what the cells are reading out are spatial patterns of slowly changing analog. There are waves, there are stable, kind of stable physiological states that sometimes move around, sometimes they hang out in the same area. um, yeah. And I think all the stuff, the kind of things that you were talking about in Earl Miller and those kind of folks are absolutely relevant to what we do. And
Yeah.
I think that's where they come from. I think these things have this like ancient evolutionary history.
Yeah. Yeah. I mean, people, the brain is a computer. The brain is an analog computer, right? Like it's way more efficient to do
Yeah.
computation with waves than anything else. Like I wonder what you think about tying in large language models and the brain. So I wrote a paper arguing that large language models don't have any agency. They don't refer to things. When an LLM spits out a fact about Einstein, it's not actually spitting out a fact.
Yeah.
It doesn't have knowledge, etc., etc. But there are people like Sam Harris who weirdly think humans don't have free will,
Right.
but he thinks that large language models do have free will, which I don't know. I have no idea how he came to that conclusion. But I liked your paper with Chris Fields about the strong free will theorem very much. And I'm kind of the mind. I bring to the table a kind of like anti-physicalist, Galen Strawson type inspired philosophy of methodological, naturalism, whereby I kind of see things this way, like, before Newton, you had a very clear definition of what is possible through the physical. Cartesian mechanics, contact mechanics, right? Intuitive contact mechanics. I mean, I've argued more recently that I think neuroscience is still in that kind of pre-Newtonian type of framework where we're desperately looking for neural mechanisms. We have to, in order for it to explain language, there has to be a mechanistic type story. And like I said, mechanisms are great, but there may be other more mysterious, causal and explanatory structures that can get you the sort of things I told you about. But so before Newton, there was a clear concept of physical. We knew what physical meant. But after Newton, Newton kind of proved that there really is no such notion as physical. Physical just means whatever physicists happen to agree on, right? Science became not about um, generating theories of the world, but just about generating explanatory theories that humans can interpret, right? Human interpretable explanatory theories. And I don't know if you would go as far as I am in terms of um, you know, this type of Fristonian type perspective, I guess, that science is really in the game of just generating interpretable theories. It's not really in the game of actually, we're trying to figure out what the world is really like. But maybe the best we can do is just generate coherent theories. And I wonder if that pertains to things like free will. And the reason I say that is because it's very common for people to say things like, oh, free will is just incompatible with biology. Well, okay, it's incompatible with like known biology. Is it incompatible with known physics? Actually, no, it's not. There are loads of things, and the reason I'm emphasizing this is because I have the same problem, not with free will, but even with things like language. Because of course, people will make the same argument for language. They'll say, "Oh, what we know, the brain is the brain does a Bayes optimal Q integration, and that's it. It's all about prediction." And I agree with the people in that part of the world. Of course, the brain does do prediction. It does do all these sorts of things. But based on our current known physics, so-called of the brain, I don't think we have any reason to sharply claim that what the brain can do is necessarily incompatible with things like syntax or free will, right?
Yeah. Yeah, I agree with that, and I actually have even kind of a weirder view where we've been, and I apologize. In a couple of minutes, I have
Yeah,
to head off to my
yeah.
doctor's appointment, but I would love to. I'd love to send you a couple things on that
Mm,
question and see what you have to say. I mean, the bottom line is that we've been looking at extremely minimal models. I'm talking about not biologicals, for example, bubble sort.
okay.
Something as simple, 5 or 6 lines of code, completely deterministic, completely transparent. And what I found is that if you treat that as a behavioral system and you come to it with not a, with if you relax the assumption that everybody makes that things do exactly what the algorithm tells them to do,
Yeah.
then you find all kinds of things that it's doing that are totally recognizable by any behavioral scientist, but are in fact nowhere in the algorithm. And
Mm.
so even something as simple as bubble sort, it has delayed gratification. It does these weird side quests that are they're not forbidden by the algorithm. I mean, it still sorts the numbers, and that's what everybody's been sort of focused on. But it does all this other stuff, and I'm starting to call it sort of intrinsic motivation in the sense that the things it does are not the things we forced it to do via the algorithm. It does other things that we didn't know. In fact, what is it, 60 years that people have been looking at sorting algorithms and nobody noticed this. And so I think all of the things that these language models are saying are possibly a complete red herring, having nothing to do with what's actually going on in there as far
Yep.
as what does the system actually want to do. And I think I'm much more interested on what these systems do that we didn't force them to do. So the language use,
Mm.
I feel like that's the algorithm. We're making them do that, and
Yeah.
I'm much less interested in things that we're making them do. I want to understand what are they doing that we're not good at noticing yet.
Mm.
That are
Yeah.
actually in spite of. So it's like this weird, it's this weird thing where I'm sort of an anti-computationalist. Like I think these kinds of systems may well have what we're interested in as far as true cognition, whether like whatever, but it's
Yeah.
not going to be because of the algorithm. It's going to be in spite of the algorithm, I think.
Yeah.
And so that kind of gives another a sort of different, the free will thing. People usually focus on determinism or indeterminism, and I
Sure.
think neither of those gets you what you want from free. I mean, randomness
Yeah.
doesn't help with that either.
Exactly.
But I think there's this third thing. This third thing is the stuff you do that is neither prescribed nor forbidden by your materials and your
Mm.
algorithm.
Mm.
And those things, anyway, I'll send you. I got to run, but I'm going to send
Okay.
you a link. We have this symposium that it's kind of this asynchronous symposium on Platonic space, and it's this. I've gotten together a bunch of people, computer scientists, philosophers, mathematicians, some physicists, and we're talking about this notion that there's a latent space from which there's a structured latent I mean, that's the hypothesis, a structured latent space from which these kind of ingressions come from. So they're not random, they're not just complexity, not just unpredictability, but there's actually, akin to the Platonist mathematicians, like this idea that there's actually a space that we can study
Yeah.
that is where these things are drawn from, would be forms of behavior, forms of anatomy, and so on. So
Yeah.
anyway, I'll send you a link. Take a look at that, and maybe let's
Please.
chat again because I'm interested in what you have to say about it.
No, no. One final quick note. That sounds a lot like what's up my street because, of course, there are properties of the universe that might not be easily deterministic or fall into the randomness category. Language, I think, seems to be one of them, right? There's a lot of aspects of language that don't clearly fit into that camp. But